1660. The evaporation of 1 mole of water at 298 Kelvin has a standard free energy change of 8.58 kilojoules. So that's represented by here. We have H2O liquid, which is coming to equilibrium with H2O gas, and the delta G is a positive 8.58 kilojoules. Now letter A. Is the evaporation of water under standard thermodynamic conditions spontaneous? All right, so let's just address letter A first before we get into B. Now basically they're saying, is this process, the evaporation of water, vaporization, right, evaporation, liquid to gas, is this spontaneous? Well, remember, there's only one unit that will tell us if a reaction is spontaneous or not, and that's the Gibbs free energy, which is delta G. Now, if we want it to be spontaneous, delta G has to be a negative value. So in order for it to be spontaneous, which means that this will happen, by itself, there's no extra amount of heat from an external source. Will this happen by itself? And the answer is no, right? Because our delta G is a positive. So, is the evaporation of water spontaneous? No. Since the delta G is 8.58 kilojoules, this is non-spontaneous. That's why at room temp, right, 298 Kelvin is room temperature. This is 25 degrees Celsius. That's why if you leave a cup of water out at room temperature, it is never going to just disappear, right? It's never going to evaporate. It's just going to stay water. Well, the reason is because it's a non-spontaneous reaction. That's why you have to put the water under a heat source in order to make that water boil. Like when you're boiling pasta, you don't just stare at the water. You got to put it under some heat and let it, evaporate, because that's the extra amount of energy that you need. But anyway, let's go on to letter B. So we already answered letter A. The answer is no, it's not spontaneous. So now, letter B, we need to determine the equilibrium constant Kp for this physical process. And maybe I will box this off just to, this is the answer. Okay, cool. So now letter B. We want to solve for that Kp. So there's only one formula between a delta G value and a Kp, an equilibrium constant. And it's this formula right here. So let's just bring this up. Now, in my formula, I just have letter K. I don't have P there, because I can solve for any equilibrium constant. It doesn't have to necessarily be the one that's pressure. Could have been concentration, Kc. Could have been Ka for acid or Kb for base. So we could just say that this is just the general equilibrium constant K. This is going to be equal to the E button on the calculator, and it's all raised to the negative delta G divided by R times the temperature. So let's see, do we know any values? Well, let's just start with R. Keep in mind that R is always going to be a constant. It's 8.314, so that's memorizable. And the units, if you're using 8.314, is joules per mole times Kelvin. So that means that your delta G has to be in joules and your temperature has to be in Kelvin. And thank goodness, they already gave the temperature in Kelvin, so I don't have to convert anything here. But that delta G value, it's got to be in joules. So before we plug any value in here, I first have to convert the kilojoules into joules. The kilojoules into joules, that's a pretty standard conversion. All you have to do is just times by 1,000. Similarly, you could just take the decimal, move it to the right 3 spots. So this essentially would be 8,580 joules. And that's the number that I'm going to throw in over here. 8,580 joules. The E's on the calculator, and I'm just going to solve for K. So let's see, K equals E raised to the negative fraction. We got 8,580, all divided by the 2 values. And maybe I will just bring this down just to exaggerate that I need to raise it. Here's 8.314. And then here's my temperature, 298. So what I'm going to do is I'm just going to simplify this value. Just get this to being one number. Then I could take the e value and raise it to that. So negative 8580 divided by 8.314. And since I'm not using parentheses, and I want to say that I want the 298 in the denominator, I have to press divide. So I'll divide by 298. And I have a long slew of number, right? Negative 3.463, and it keeps going on and on and on. Now, since this is not the final answer, I'm not going to round when I do my calculation. So k equals, I'm going to say after I do that, okay, second ln, that's where your E button is. Now, I love the TI-84 because I could just go up, grab the whole number, boom, there it is, less chance for error. I'm just going to press enter, and there you go. We'll do, I guess, 3 sig figs. So 0. Actually, I guess I'll do this in scientific notation. 3.13 times 10 to the negative second. No units for any equilibrium constant. And since they said it was specifically a KP, I'm just going to strap on that P there and call it a day. And that is your equilibrium constant for this. And it kind of checks out. It definitely checks out. If you have a non-spontaneous delta G, your Kp or any K value has to be less than 1. So, checks out and we're done. Stay tuned because I think there are more parts for this question. So hang tight if you guys are on the playlist, which I highly recommend you are. I'll see you in about 5 seconds. In the meantime, if you wouldn't mind, please hit the subscribe button to just help us get the word out there in the YouTube universe that this free educational channel exists. I think it's pretty cool. It's helping out tons of people. We're almost at 25,000 subscribers, and it's absolutely insane. But I'm really glad that we can help you guys out, and let's just keep learning. I'll see you in a few. Bye-bye.